So let's resume our study of the natural numbers. So far we've defined succession, next, and we defined these number symbols, although they're actually not all that useful, except for 0. And we have defined the natural numbers, and then we established this mathematical induction, which is the real essence of the natural numbers. This is what we use pretty much to prove all of the different properties of natural numbers. And we defined an ordering, less than or equal to, and these are sort of the fundamental facts about those that we use throughout our proofs. We established some properties of 0. So 0 is sort of, these are the same here. 0 is the least natural number, and nothing comes before 0. So 0 is not the next of anything. And now we're here. This is a theorem about succession and order. Order refers to this symbol, and succession refers to the next symbol. So order refers to this, and succession refers to this. And this theorem is about the interaction between them. And preserves order, this is a phrase you will see used very often in mathematics, and it refers to operations or things you can do to things that basically that preserve order. So here succession is next, and preserves order means when you do next to both sides of an inequality like this, the inequality remains true. So if m was less than n, then next m is less than next n. So this part 2 here is what I would call succession preserving order. Part 1 is a little bit weird looking, and it's mainly there just because it's what we will directly prove, actually. Part 2 is equivalent to part 1. So you can see, let me go back up here to essence of order and succession. Remember, we're going to use these two a lot, so it's good to just have them sitting there in your brain in working memory, ready to be used at any time. Anytime you see less than and then a next, imagine mushing these together, and that's the same as less than or equal to. It's not the original definition. Less than or equal to is defined like this, but it's a thing that we immediately prove. So yeah, that's what's going on between number 1 and 2. 2 is just 1, except the less than or equal to has been expanded to look like a less than. If I'm going to remember theorem 99 in any way, I'll remember part 2, since it looks like succession preserving order, right? You're taking an inequality and then you're slapping a next on both sides, and the inequality is remaining true. What we're actually going to prove is 1. And that will prove 2 because these two are equivalent. All right, so here I have theorem 99.1 ready to be proven. And it's an if-then, so it assumes n is a natural number and m is less than n, and then I want to prove next to m is less than or equal to n. I'm including this n is a natural number part because it's easy to miss, so be careful when you read these. It is up here, so it's right here. The reason it's here is because it's a global assumption for this whole theorem. I mean, I guess both parts actually say m less than n, so the assumption m less than n could be up here too. I'm not sure why it's not. That's just the way I wrote it, I guess, but yeah, so all I did was move this assumption to here. Okay, so I'll start by assuming the hypotheses. Assume n is a natural number, m is less than n, and then I want to prove this, except that's already the wrong thing to do. So if I try to do it this way, and now my goal becomes prove next to m less than or equal to n, I'm going to have a lot of trouble just proving this. I don't really have much to go off of. Instead, the way I should look at this is that I'm trying to prove that a certain thing is true about all natural numbers n. Somehow I'm supposed to use this assumption that n is a natural number, right? Like, how do I use that? Am I going to go back to the definition of natural numbers and then try to use axiom 5 on the original definition? That seems to be what I'm shooting for here, right? If I'm just going to assume n is a natural number and then try to go from there. That's a bad idea. instead, mathematical induction should be the way that we prove that natural numbers have certain properties. In this case, it's just a complicated to write down property. So let's get rid of this stuff. And I'm even getting rid of assume n is a natural number. I'm even getting rid of that because I don't want to fix n, actually. I'm going to do induction on n. So let me state clearly what I'm going to prove by induction. So we will prove by induction that, and then when you're proving something by induction, it always has this format, that it's proving that for all natural numbers, and then a certain thing is true about n, right? So this is always the format of what you're going to prove by induction. Sometimes actually the way you'll see it written is without the universal quantifier. Like here we will prove blah blah blah, but then there's the universal quantifier. It's just not written on the same line or whatever, but it's there in words. So the only thing I'm doing differently here is writing it explicitly on the board here. So when we go to apply this theorem, mathematical induction, what we're trying to prove has this form. That's why I'm starting like this. So I'm starting like this so I can figure out what's going to be my phi in this situation. So phi will be some proposition that has probably some x's in it, and those x's will get replaced by n here in the thing that I'm trying to prove, and the x will get replaced by 0 and n and next n in different positions. So what is it that I'm trying to prove for all n? I'm trying to prove that if m is less than n, then next m is less than or equal to n. That's what I'm trying to prove. So then this is my phi, sort of. It depends on how you name variables, but if you're going to use this exact statement of the theorem mathematical induction, then this one uses x's as the thing that's getting replaced by different things in different positions. So what's really my phi here would be, let me write it in kind of a scratchwork zone. Phi is m less than, so what is it that's going to get replaced? This thing in yellow is supposed to be phi with x replaced by n. So I'm going to put x's there so that they can get replaced by n. This is what I mean when I say we're doing induction on n. I mean, that's the position where the n was is where I'm putting an x here. That's the position, the variable that's going to get replaced by 0 for the base case, and by n for the induction hypothesis, and by next n for the goal of the induction step. So these are two ways of saying the same thing. We can say our phi of the moment is this, where the x is like this, or we can say we are going to prove that this is true for all n by doing induction on the variable n. Okay, now that we're clear in our scratchwork about what phi is, there's no doubt about what must be done. The base case is phi with the x replaced by 0. So m less than, and then I put 0 instead of x, implies next m less than or equal to, and then I put 0 instead of x. And then the induction step, let me just write this for short. No doubt. What we have to prove in the induction step is that, well, we basically have to prove this, right? So we say, suppose n is a natural number, then assume the induction hypothesis, and then attempt to prove this. So suppose n is a natural number, and then I like to put the induction hypothesis in the same sentence often. Suppose n is a natural number, and then I immediately assume, what's the induction hypothesis? It's this. It's pretty much actually the thing in yellow. So basically phi with x replaced by n. Now it's an assumption. And then now we must prove, so the goal becomes this part, right? That phi holds when x is replaced by next n. So we must prove m less than next n implies next n less than or equal to next n. Okay, let me make some room for the base case. So how do we prove the base case? So we need to prove this implication, and that means we should assume m is less than 0 and then attempt to prove next to m is less than or equal to 0, right? But, well, there are a couple of ways of looking at this. One way is, hey, m is less than 0 is always false, actually, right? Nothing is less than 0. One way to see that is less than is actually membership, and 0 is the empty set. So here you see less than is actually membership, and here you see 0 is actually the empty set. So because the empty set is empty, this is false, which makes the implication vacuously true. Okay, so I filled in that argument. M less than 0 is equivalent to m in the empty set, which is false, and so the implication is true. Now let's do the induction step. Now I don't think I'm going to get away with the same trick. I need to prove this implication. I don't think I'm going to try to disprove the hypothesis and then get the implication is vacuously true. I think this hypothesis can sometimes be true. So let me assume the hypothesis here, and then try to prove the conclusion. And remember the entire time that the induction hypothesis, this overall implication up here, is available to me. Okay, so in order to prove this goal, okay, so do pay attention to the setup here. We have this implication. We're trying to prove this implication. So keep that in mind. So in order to prove this one, I'm going to assume this. Now, I see, okay, so one thing that you can do when you get stuck during the induction step is remember that you have your induction hypothesis available. So try to arrange things so that you can use it. The induction hypothesis here is an implication, and to make use of an implication, you need to be in a situation where the hypothesis is true, right? Then you can deduce the conclusion. So to make use of my induction hypothesis here, I would like to put myself in a situation where m is less than n. Am I actually in that situation? Well, not necessarily. I have that m is less than next n. So if I imagine, putting dots in succession for natural numbers, maybe n is here, next n is the next dot, right? And then what I know about m is that it's strictly to the left of here. M is somewhere over here. Not there, somewhere over to the left. And there's a bunch of stuff here, and somewhere there's the dot labeled 0. Now, if I have that m is less than n, if I have this, then I can make use of my induction hypothesis. So if I knew that m were actually to the left of here, then I can use my induction hypothesis. But I don't know that it is, right? It could be that m is to the left of n, or it could be that m is right there equal to n. So that's what the picture suggests, at least. So it seems like we're going to end up in different cases. And one of the cases will have m being to the left of n, and another case will have m being right there at n. So can I actually get this case split that appears in my picture or in my imagination? Can I get this case split into the proof? What is this case split all about? It's about m either equals n or it's less than n, right? Either m is equal to n or it's less than n. In other words, this is the or statement that my case split would be all about. This is an or statement, right? This is less than or equal to. But that's essentially what I have here, right? The less than with the next symbol next to it. Those mush together to become this symbol. again, it's not by definition, but it's by this theorem you proved on your homework, which immediately follows from the definition, pretty quickly, this theorem. So now I know my next step. It'll be then, from m less than next n, m is less than or equal to n. And this is an or statement, so let's just make it clear that it is an or statement. So m is less than n, or m is equal to n. That's the actual definition of less than or equal to. So now we have cases. And in case one, that's the case where I get to use my induction hypothesis, right? So I could say by the thing over here that I assumed over here, but that's pretty messy and pretty hard to write in LaTeX, right? So by the induction hypothesis. That's what this is called. We have next m, so this is my conclusion, this is what I get, is less than or equal to n. Now my goal is to prove next m is less than or equal to next n. So my goal is actually an or statement, right? Prove either that next m is less than next n, or that next m is less than or equal to, or that next m is equal to next n. So one of these two, basically the or that's built into that's less than or equal to. So I can prove either one of them, and that would be sufficient. Here I have, I think, one of them, because this less than or equal to can be expanded into a less than next. So next m is less than next n. Okay, that's one of the two sides of the or that I'm trying to prove here. So next m is less than or equal to next n. So all I'm using, this is kind of sometimes a confusing step, all I'm using to go from here to here is pure logic. Nothing fancy about our definitions, just the fact that if you have that phi is true, then you can deduce phi or psi, this feature of or, that having one side lets you deduce the or. Now what about the case m equals n? Then let's write down what we want to prove. Then how about our goal, let's call it. Our goal becomes next m less than or equal to next n. If m is the same as n, then this is equivalent to next n is less than or equal to next n. But this is true, because they're equal, right? This is again that same logical principle. We prove now this time the other side of the or. If you prove they're equal, then it's true that they're either less than or equal. And that's it. So a concluding sentence is not really needed, since I already made it very clear what it was I needed to prove by induction. I proved the base case and I proved the induction step. That's it. That's it for succession preserves order.